Newtonian mechanics, the basis was all inertial frames. All inertial frames are equally important or are equivalent in describing dynamics. What do you mean by inertial frame? We defined in the very first lecture, probably, which is a frame that is either stationary, right? Or what? Anybody remembers?
Moving with constant.
Very good. Moving with constant velocity. So if you have two frames, like this frame, for example, X, Y, Z, we're going to call it frame maybe I, or frame A. I is fine. Now we have another frame. This guy is moving with constant velocity. Okay? This frame is maybe I prime. Okay? And if you have particle moving here, particle moving there, indeed the equations of motion, here is simply force equal mass times acceleration. Here it's force prime, the force that we feel in this frame, equal mass times the acceleration that we measure in this frame. So the equation of motion is written in the exact same way in each frame as long as they are inertial frames. If anyone is accelerating or rotating, because rotation is associated with acceleration, right? So it will not be an inertial frame. But if they are inertial frame, they will perceive, they will observe the same forces, F equals F prime, of course the same masses, and they will perceive the same acceleration, because this is moving with constant velocity. If you differentiate it to get the acceleration, it will not matter, right? So this was the underpinning principle in Newtonian mechanics. Over there in Maxwell equations, the main assumption, or the main outcome actually, Maxwell equation implies that the speed of light is constant, fixed constant in all reference frames. Okay? So if you have a reference frame in which you want to write down Maxwell's equation, the speed of light has this value. Another reference frame, and you want to write down the same Maxwell equations, describe the same physical phenomenon, it has to have the same value for the speed of light. This immediately contradicts with this guy. Why? Because if you have here a phenomenon or some light source moving, here is not moving, here is the light source, and here is the light moving with speed c. Okay? If you are an observer over there, so over here we observe this phenomenon or this wave traveling with the speed of light. That's fine. That is stationary. This guy traveling with c, we indeed see it traveling with c. And over here, if I'm an observer here, I will observe this guy traveling with c minus v, right? So now the speed of light here is c, but the speed of light here is not c minus v. To Newton, these are two inertial frames, two reference frames. They are good to describe the physical phenomena. To Maxwell, they are not. So at the beginning of the 20th century, this contradiction was problematic. Simply, you cannot satisfy both Newtonian mechanics and Maxwell dynamics at the same time. Okay? So this is the problem. They are in contradiction with each other. The solution was by Einstein. 1905, when he laid down the foundation for special relativity. He said, well, he has very big statements that are really inspiring. There's no time to mention them. But at any rate, he said, nothing of the classical and fundamental work can reconcile these two theories. You cannot do that. And he did something extremely simple, but very bold at the same time. He said, well, how do you transfer coordinates from here to there? Well, we say we do that by saying, well, any x is the same as x prime, maybe plus or minus vt or something, right? So any coordinate x here, assume that they start at the same orientation, same point, and then this guy travels with the velocity v comes. So any point measure with respect, any x coordinate here will be the x bar, x prime coordinate there, plus vt, right? So, and you transfer the time is the same. Well, time is absolute. Time here is time there, right? This guy is just traveling. So the main thing he said, well, you can never reconcile these two things because they simply contradict each other if one is moving. You can never reconcile these two things unless you say that the time is not absolute anymore. When you transfer space, you transfer time such that the rate of change of space with respect to time of a light wave remains the same. That's it. This is the main assumption of special relativity. Nothing more. And the transformation that he did when he said, okay, I'm going to transfer, not only transfer space, but only I'm going to transfer time. So this is not any more t prime. It's something times x plus something times t. The same here, something times maybe d, e, okay? Just linear transformation. The mathematics in special relativity is extremely simple. Linear transformation between space-time here to space-time there. But it's the boldness that you stop and say, hey, physicists, all what you have been doing so far is not actually correct. And you know what? Time is not absolute. Time is really relative. The time that takes for a phenomenon for an event to occur here is different from the time that it takes the same phenomenon to occur there. Just by the fact that this guy is moving. Okay? So this boldness that gets him the special relativity. But the mathematics is indeed simple. This is not the case with general relativity. General relativity is very complicated. But this is the mathematics of special relativity, just linear transformation. What is the main conclusion? The main conclusion is that our world is not 3D anymore. But 4D, space-time together, they are lumped together. Okay? If you have the space here, you should have the space here and x coordinates, and you want to know the space there. This is not enough piece of information. You should tell me the time as well. The space-time is lumped together. If you have them, I can tell you the space-time here. Okay? I cannot transfer space only. You have to tell me your time stamp as well. So this is the main outcome of special relativity. Now for you, as someone who studied dynamics in this way, so for Newton, this was a problem. I mean, Newton was dead, but for Newtonian mechanics, this was a problem. And changed everything. So the momentum, for example, is not anymore mv, but mv divided by square root 1 minus v squared over c squared. Everything changes. Kinetic energy changes, momentum changes. Okay? Just by the fact that, no, space and time are lumped together. Okay? So for Newtonian mechanics, significant changes have to be made to reconcile with this new fact or new observation. For you, as someone who studied dynamics in this way, if I'm telling you, okay, just here is your world, what are your equations of motion? What are your trajectories? What they will look like? What do you think?
For on Earth? Right.
I don't care. I mean, some crazy guy told me that, you know what? Here is Newtonian mechanics, was 3D, right? This is Newtonian mechanics. Some crazy guy told me, no, your space is not 3D, your space is actually 4D, is x and time going on, lumped together. To you, how can you write your equations of motion?
Another equation will come.
Yeah. Okay, what is the main principle?
Rate of change of momentum is force.
This is Newtonian mechanics,
But-
which doesn't work anymore unless you modify your definition of momentum. This is the problem. For you, as someone who studied dynamics in this way, how are you going to write down your equations of motion?
When we write the position vector, we add a key.
No? I don't care. It's straight line. It's straight line. Give me your manifold. It's straight line. My trajectories are straight line in the new space, in the 4D space. That's it. My trajectories are geodesics of the kinetic energy in this 4D space. Give me your kinetic energy, your new kinetic energy or whatever, I don't care. Give me your kinetic energy. It will represent a Riemannian metric, right, on this 4D space. And my trajectories are indeed simply straight lines on that 4D space. Actually, Einstein didn't say that in this paper. What he did in this paper is to come with this conclusion. Okay? Any question about this? Any question? That you will change nothing of your conceptual understanding of dynamics. Nothing will be changed. You change the space, I'm fine. It's still a free particle will indeed evolve on a straight line. That's it. Okay? General relativity is a bit more involved. Any questions? So this is why we're saying Newtonian mechanics failed at large scales where this absolute time is no longer valid. So Newtonian mechanics fails. But this analytical mechanics point of view, this geometric mechanics point of view remains valid. You change, literally, you change nothing of your main fundamental concept. General relativity is now a theory of this gravitational theory. So now we have a gravity field. There are some ways how to account for any potential function within this framework or any framework. You simply, in particular this framework, you can consider your mass as a little bit more heavy in the presence of some potential field. But let's just focus on here. The issue is, in the presence of gravity, c, the speed of light, is not constant anymore. So physicists observed that in the presence of gravitational fields, the speed of light cannot be maintained constant. Okay? Or gravitational fields bend light arrays. So this is another problem. How can we reconcile this? Another thing is the observation by Einstein, which is a very simple observation. He said, well, you know what? If you are in an elevator or a rocket or something, and this elevator, you are right here. Okay? And this elevator in the presence of gravitational field. Versus the same elevator, but now it's an elevator or a rocket ship, whatever. So now it's going up by an acceleration equal to the gravity in the absence of gravity field. So here we have gravity, okay? Gravity field. This guy is stationary, just sitting there, but there is gravity, like what we have here, okay? Versus where maybe on a place where there is no gravity, on the moon or so, and you're moving upward with an acceleration equal to gravity. His claim or his observation was, if you are inside, you will not be able to tell the difference. Anything will look to you happen the exact same way. If you have maybe a ball here, if you are stationary in the elevator, in a gravity field and you just leave a ball, it will just fall down, yg, correct? Approach the ground of the elevator. And in the same way here, if you have a ball here, just free,
It goes down.
it will go down, for sure. It will not do anything, the ball, but you're going up, right? So to you, as inside, you will see the ball, any dynamic observation will be exactly the same. So he said, this is his equivalence principle, what he called the equivalence principle. But he was very smart to take it more deep. On a deeper level, this means that gravity is not an external force. Gravity is just a type of acceleration. Right? In other words, when we will write down our equations of motion, this is our equations of motion. Mass times acceleration plus centripetal forces is 0. The right-hand side, we always tend to do that. Mass times acceleration equal forces. The gravity is in the right-hand side, is with the external forces. It's an applied force. So the gravity should be in the right-hand side. But he said, no, the gravity is just one type of acceleration. It's like this centripetal acceleration, for example. Okay? So indeed, it has to go with this set of accelerations. And a particle moving in the field of gravity, in a gravitational field, is nothing but a free particle. So this is indeed 0. But, okay, where is the term? Where the term will go? This guy, do you have, or this guy does not account for gravity. That's right, the stuff that we know do not account for gravity. How do you write this equation of motion? This is, now he used differential geometry, he used this language. So in the special relativity, he didn't do that, he didn't make any clue of this. Okay? He just came with the conclusion that it's 4D space. Okay. And it's flat space, by the way, no curvature. It's still flat space, but it's 4D. This equation of motion, we know it. It's x k double dot gamma I j k, right? X I dot, x j dot. And these gammas, where do they come from? Where do they come from? G, right? G is our Riemannian metric. So here it's a matrix. Can you tell me what's the dimension of this matrix? In this case, what's the dimension of this matrix?
2 by 2 cube.
You think it's 2 by 3?
3 by 3.
Sphere? 3 by 3?
4 by 4.
4 by 4 for sure.